Alright, let's look at section 5.6, graphing linear inequalities in two variables. Let's consider this situation. Mr. Calden is playing a game of basketball in which every made shot is worth either 2 points or 3 points. Standard game. No free throws. The game is over once he scores 42 or more points. If he's still playing now, how many of each type of basket has he scored? Now, this normally seems like the type of thing that would have one answer, except there's kind of a lot of different things we could think of. Maybe he hasn't scored at all, still 0 points on the board. Maybe he's just scored one of each. Maybe he scored 5 2-pointers and nothing else. Or 2 3-pointers and 6 2-pointers. These are all possibilities. So there's really no easy way to know this. All we can do is we can express all of the answers using an inequality. I'm going to start by writing something that looks like an equation, but I'm going to use an inequality symbol to make it special. So I know I could get 2 points for some baskets, so I'm going to call that maybe 2x for the number of baskets that I made that are worth 2 points, plus 3y based on the 3-point baskets. And now the thing to keep in mind is the game's over once the score reaches 42 or above. So since I'm still playing, that means I mustn't have 42, I must have less than 42. And so this is an inequality with two variables that expresses this relationship. Now, we can't solve just for one variable here, but we notice this looks kind of like the standard form of a line, so maybe I'll try to put this in the slope-intercept form. Start by subtracting the 2x. So I'm going to have 3y is less than negative 2x plus 42. Then I'll divide everything by 3, and I have y is less than negative 2/3 x plus 14. Alright, so now I have that. Since that looks like slope-intercept form, I'm going to go ahead and graph this on a coordinate grid. Just using slope-intercept form, start at a y-intercept of 14, then use rise over run of negative 2/3. So you can either do that by hand or use something like Desmos. So let's see what happens. Alright, so what I've done is I've used Desmos here to graph my boundary line. Now originally my inequality was 2x plus 3y is less than 42, and I rewrote that as y is less than negative 2/3 x plus 14. So you can see I've labeled the 3-pointers and the 2-pointers based on my x and y values. And I have my line here. Alright, so you can see I have the y-intercept of 14 and then a slope of negative 2 over 3. Alright, so you can see that from there. Now my boundary line is dashed, and here's the reason. Anytime my inequality is a less than or a greater than, I want to use a dashed line because I don't want anything on the line to be counted as an answer. For example, this point right up here, the point 0, 14, that would mean 14 3-pointers, 0 2-pointers. That would be a total of 42 points, which would mean the game is over. We know that that's not the case here. So anything that's on the line is not actually going to be a solution. That's why I have to use it as a dashed line. If my inequality had a or equal to underneath, then I'd use a solid line. Whether it's less than or equal to or greater than or equal to, I'd fill in the line and make it solid, because then it would be good. That's what I'd want. So now what I have to do is I have to pick a test point that's not on the line. I can pick anything that's not on the line. So maybe I'll pick this point right here. So I'm going to take the point 15, 10. What I want to do is I want to plug it into the original inequality to see if this is true. I want to see if this is a possibility. So I'm going to plug in, that's going to be 2 times 15 plus 3 times 10 is less than 42. So that's 30 plus 30 is less than 42, and that's 60 is less than 42, which is obviously false. That's no good. That means that 1510 is not a solution to this inequality. And that would be pretty clear, because that would mean I actually would have scored 60 points, which would have ended the game. So since that's not a solution, I want to pick a test point maybe from a different area. Perhaps I'll pick this point down here. So picking the point 5, 5, I want to see if this is true. So I'm going to plug this again back into my original inequality. That's 2 times 5 plus 3 times 5. I want to see if that's less than 42. Well, that's 10 plus 15, which is 25. Is 25 less than 42? Of course it is. That means not only is 5, 5 a solution, but everything on this side of that boundary is a solution, which is pretty remarkable. So what that means is I'm actually going to shade in this entire region. So I'm going to shade here. You want to get as close to the line as you can without going crazy here. It's okay if you touch a little bit when you're making the shading. But this is what you do. Every point over here is actually a solution. That's what's amazing. We said there were a lot of possibilities. This is all of them. And it would extend on forever. So this point's a solution. This point, this point, this point, this point. All of these points are different solutions, different possibilities. So there's no way to say that I definitely had 5 3-pointers and 5 2-pointers, but it's one of the possibilities that the game is still going on. Anything over here that's not shaded is not a solution. So that's how you determine how to shade. You check a test point in your original inequality. Now, just one last thing I kind of want to point out. It may seem a little silly, but we do want to consider the limitations on this. We've talked before about discrete and continuous graphs. The same thing can happen with inequalities here. With the shading we did there, it showed that everything below or to the left of the line was a solution. But that includes negative numbers, that includes decimals and fractions, and in reality we know we're talking about the number of baskets being scored. So we're actually limited to only whole number values, something like 0 3-pointers, 1 2-pointer. That would be okay, or something like this right here. So there's all these different points that are on the grid. And there's a lot there. I'm not going to color them all in, but we couldn't ever go negative in either axis here, and we couldn't ever be in between these boxes because that would indicate that we have a fraction of a basket made. Certainly we can have 0, but otherwise it has to be non-negative and it has to be an integer. So that's what it is. We have limited possibilities, not quite infinite, but there are a lot of different possibilities for the number of baskets that Mr. Callan made in either 2-pointers or 3-pointers. All right, hope this makes sense.